All right, I'd like to welcome everybody to this special online class in order to make up for the week that we missed during the snow apocalypse. And this is going to be our first intro to Chapter 5, Introduction to Hypothesis Testing. So this is finally where it all is going to happen. So all of the work that we've been putting in, sanding the floor, learning about means, learning about standard deviations, all that work that we put in, painting the fence, learning about z-scores, and all that work that we put in, learning about probabilities and the normal curve, and all the practice that you did in order to make it very, very fluid, in order to make it very, very practiced, all of that is going to come together today in our look at hypothesis testing. So we're finally getting to the cool parts of statistics where we can really do some statistical, psychological work, the kind of cool stuff that we do as psychologists every single experiment that we look at. And also, not too far off on the horizon, when you're doing your capstone course or your advanced lab, this is going to be the skills that you're going to use to analyze data that you're going to collect. So it all begins today with our look at hypothesis testing, and this is what we're going to be doing for the remainder of this semester. The remainder of this semester is going to be dedicated to different types of hypothesis testing, and it all starts today. All right, so let's set it up with a example here, theoretical example. So let's say that you graduate from IUSB and you go into educational psychology, and an elementary school calls you up one day and wants you to take a look at their students. So they feel that their students are lacking in confidence, they're lacking in self-esteem, and they want to know if there's anything that you can do to help their students. So let's say that you take a look at this program and you notice that they have a very, very traditional physical education program. They have a very traditional physical education program that uses a lot of drills, a lot of push-ups. And you, because of your training in psychology, have developed a new treatment, a new way of doing physical education that's based on gameplay. So the students are still exercising, but now you're basing it on gameplay. And let's say that you then treat a classroom of these students with your games intervention. You let them remodel their curriculum to implement your games theory. At the end of that semester, you can measure the self-esteem of these students. And what we want to know is, does the self-esteem of your students, is it higher than the population of students that are doing a standard physical education program? So we could definitely tell for your sample of students whether or not they're higher than the population of students. But what we're going to see today is we're going to see a way of generalizing from your sample to be able to answer the question of, if you applied this treatment to the population of students, would they be better than in the traditional education program? So this is going to be our first time where we take a look at the tools that we're going to use in order to generalize from a sample of students to an entire population of students. All right, so the logic, the outline today, we're going to take a look at the core logic of hypothesis testing. We're going to take a look at the 5-step hypothesis testing process, and then that's it. That's going to be our intro to this, and we're just going to kind of let it absorb, let it work through, because this is the key thing for the rest of this semester. All right, so the core logic of hypothesis testing. Hypothesis testing is a systematic procedure for deciding whether the results of a research study support a hypothesis that applies to a population. Another way of saying that is that hypothesis testing is what allows you to take the results from a sample and intelligently, ethically, correctly infer things about an entire population. It's what allows us as psychologists to say, I found this for my sample, and this result, this effect, this treatment will work for the entire population. Or it lets us decide, I found these results for my sample, but this treatment, these results, this intervention will not work for the entire population. That's what allows us to make that decision. So one of the key things to remember here is that researchers who are doing a study, they always want to draw conclusions about a population that they're studying. So they take a sample from the population, but they always want to draw conclusions about the entire population. So if you have a sample of students, such as we do in this example, a sample of students in a physical education program, you don't want to just draw conclusions about those students. You want to draw conclusions about all students in general. And these conclusions, again, they have to come from results that are based on studying a sample of students. Now, typically a sample will be more than just one subject, but just to kind of give you a heads up, in your textbook, in order to introduce the idea of a hypothesis testing, they will start off with samples of size 1, samples where there's only one subject. So just bear that in mind. We're going to start off with a sample larger than 1, just so that we can get the correct way to do it right off the bat. But just bear in mind that in your homework, in your textbook, they'll often say, oh, you have this one subject, this one score, and they'll use that to introduce the idea of hypothesis testing. It's the same logic, it's the same idea, but we're just going to introduce the use of a sample right off the get-go. So again, we know things about a sample. We want to draw conclusions about a population. All right, so the key here is that the original population that we're working with, for this introduction to hypothesis testing, we're going to assume that that population is known. So we're going to assume that we have a known mean and we have a known standard deviation. Now, in reality, this is very rarely the case. However, it makes it a lot easier to introduce the ideas of hypothesis testing. So we're going to start off with these easy to do hypothesis tests that might not come up very often in the real world. And then as we build our skills, we'll generalize to actual more realistic cases. But just for right now, just so that we can introduce this strategy, we're dealing with a known population, meaning that we're dealing with a population where we know the mean of the population and we know the standard deviation of the population. And what we want to ask, what we want to find out, is that if we applied a treatment to that entire population, will our treatment change that population into a new population that has a new mean and it has a new standard deviation? So that's the question we're trying to answer. Does our treatment work for the entire population? And if a treatment works, that means that it changes your population into this new population, this new treated population. And we don't know how big the change will be, which is why we have this unknown mean in our treated population. Now, that's what we want to know. Will our treatment work for the entire population? That, however, is something we just can't do. We cannot just apply a treatment to the entire population for a variety of reasons. So what we do is we take a sample from that known population. We take a sample from that population we know things about, and then we treat that sample, and then we see afterwards whether or not that sample has changed enough in order for us to conclude that it now belongs to the treated population. It's changed enough because of the treatment that it now must come from or must belong to this new treated population, indicating that your your treatment works. So that's a general idea. A couple of more things we need to establish here. First off, one simplification we're going to use is that the standard deviation of your treated population, we're going to assume that that is the same as the standard deviation of your original population. So in other words, our treatment is simply going to move the mean of the population, but it's not going to do anything to stretch or squeeze the distribution of this population. It just affects everybody in the same way. So that's just a simplifying assumption that makes the math easier, especially when it was grad school students locked in their ivory towers with stacks of paper and pencils trying to do this statistics by hand. This cut down on a lot of math. So that's the only reason we're going to make that assumption. So this is what we want to know. When we take a sample from a known population and we treat it, does that treated sample now belong to this new treated population, indicating that our treatment is effective? Or has it not really changed very much and it still belongs to that old known population? That's the decision that we're going to be making. Now, the last thing that I'll point out for those of you who are critically thinking about this, one thing we're not going to do to begin with is we're not going to measure this sample initially. This sample from the known population, we're not going to measure that sample. And that seems rather counterintuitive. That seems like something that should be done. And you're right, it should be. But again, this is just a simplification that we're doing in order to introduce the core logic of hypothesis testing. So we're going to take, again, a sample from a known population. For some reason, we're not going to measure it. We would in real life, but here we won't. And we're going to treat it, and then we're going to measure the sample after treatment. And we're going to determine whether that sample after treatment belongs to a new treated population, or does it belong to that old known population? And again, if it belongs to the new treated population, that means your treatment changed your sample, and that's it, that it's effective. However, if the sample still belongs to the old known population, that means that your treatment did nothing, and that's the conclusion that we'll come to. All right, so the hypothesis testing procedure. The nice thing about hypothesis testing is that it's a 5-step procedure, and this is the same 5-step procedure that you're going to be doing for all of these hypothesis tests. So for the rest of the semester, these are going to be the 5 steps that you're going to go through whenever you're testing a hypothesis. So step number 1, we'll introduce the steps and then we'll go through them in detail. Step number 1, restate the question as a research hypothesis and a null hypothesis about the population. Step number 2, determine the characteristics of the comparison distribution. Step number 3, determine the cutoff sample score of the comparison distribution at which the null hypothesis should be rejected. Step number 4, determine your sample score on the comparison distribution. And then finally, step number 5, you make your decision whether to reject or accept the null hypothesis. So these are the 5 steps. Let's start taking a look at them in a little bit more detail. So step number 1, restate the question as a research hypothesis and a null hypothesis about the population. So we always have a question that we're trying to answer. And typically, the question is something along the lines of, is there a difference between the treated population and the known or untreated population? So is there a difference between the population that received the treatment versus the population that is untreated? And that's all we ever want to know. If we apply a specific pill to the population of depressed people, do they then change into undepressed individuals? If we do behavioral cognitive therapy with people with the population of phobias, do they then change into a population of non-phobic individuals? So that's what we want to know. Is there a difference between the population before it was treated and the population after it was treated? So that's the question we want to know as psychologists. Unfortunately, the way that it's stated right now, it cannot be answered by statistics. So in order to let statistics apply and work on this particular question, we need to restate it in a way that statistics can get a hold of it. And that's where the research hypothesis and the null hypothesis come into effect. So the research hypothesis, this is the idea that the treatment, or the hypothesis that the treatment does have an effect. So the research hypothesis is a hypothesis that says your treatment works. And the way this is expressed is by saying that the mean of the treated population does not equal the mean of the untreated population. So this is what it means to say that a treatment works. This is what it means to say the average level of depression for the treated population does not equal the average level of depression for the untreated population. The level of phobias for the treated population does not equal the level of phobias for the untreated population. So this means that your populations are different. So the treated population could be higher than the untreated population. That would be the means do not equal each other. The treated population could be lower than the untreated population, the original population. That still means that your treatment has caused an effect. Clearly, though, it has to be different. So that's what this research hypothesis says. The treatment has an effect because the mean of the treated population is different from the mean of the untreated population. So that's the research hypothesis. The other hypothesis is the null hypothesis. And the null hypothesis is always the complete opposite of the research hypothesis. So the research hypothesis is that the treatment does have an effect. The null hypothesis is that the treatment does not have an effect. The treatment does nothing. And we phrase that, or we write it mathematically as the mean of the treated population equals the mean of the untreated population. So if the mean for these depressed individuals was 42.5 on Beck's depression inventory, and after treatment, the mean was 42.5 on Beck's depression inventory, the means were equal, well, your treatment does nothing. If people are this afraid of heights before your phobic treatment, and after treatment, they're still this afraid, well, your treatment has done nothing to cure their phobias. So if the mean of the treated population is the same as the mean of the untreated population, that means that your treatment has no effect. Your treatment does nothing. So we have two hypotheses here. We got the research hypothesis. Your treatment does have an effect. The mean of your treated population is different from the mean of your untreated population. And then we have the null hypothesis that says your treatment has no effect. And that means that the mean of the treated population is the same as the untreated population. And one last thing to notice about this is that the research hypothesis and the null hypothesis together have to cover every single possibility. So there's only three things that can happen when you treat a population. Either the scores go up, or the scores go down, or the scores stay the same. So in this case, there's three things. They can go up, they can go down, or they can stay the same. Those are the only three possibilities. The null hypothesis takes care of the scores stay the same. The research hypothesis takes care of the scores go down, and it takes care of the scores go up. So all three possibilities are covered, and that's one of the ways to know whether you did a null and research hypothesis correctly. All three possibilities, going up, going down, and staying the same, have to be covered by one of the two hypotheses. All right, so that's step one. States a question as a research hypothesis and a null hypothesis about the population. Step two, determine the characteristics of the comparison distribution. This comparison distribution, it is a distribution that stands in for or represents the population distribution if your null hypothesis is true. So this is the comparison distribution that stands in for the known population. And it's a known population because this is the comparison distribution for if the null hypothesis is true, if your treatment changed nothing. So this is a distribution that you compare your sample score based on your measurement of the sample. So it's important to realize for this, going forward in this course, that this comparison distribution represents the population distribution. It is not the same as the population distribution whenever you have a sample that is larger than 1. And it's a distribution to which you compare your sample's results. So you need a distribution where you can take your sample mean and compare it to a distribution of the same thing. You need to be able to take your sample mean and not compare it to a distribution of individuals like a population. You need to be able to compare it to a distribution of sample means, and that's why we introduced the idea of the distribution of sample means last time. So if you recall the distribution of sample means, it only looks like the population distribution. It only looks like this population distribution when you have a sample size of 1. But once you start having sample sizes of 2, 3, 4, and 5, it goes away from looking like your population distribution, and it looks like a normally distributed distribution. So that is the characteristic of, that's the comparison distribution. It's that distribution of sample means. Now your book is going to let you use the population distribution for the time being, because they start you off with sample sizes of 1. But just because we're going to be making this switch later on, I'm going to teach you the correct way first. Keep it in your mind so that when we make the switch in chapter 6, you won't get confused and basically have learned it incorrectly using the population. Remember that the population is not the correct distribution if you have a sample size more than 1. You need to compare your sample mean to a distribution of sample means. That's the only fair comparison. You can't compare a group to individuals. You got to compare group data, a sample mean, to that distribution of sample means. So keep that in mind. It's going to become more important later in this course. All right, step number 3. Set a cutoff sample score or a critical value. This cutoff sample score is the target with which you will compare the results of your study. This is what I like to call your line in the sand. So we're going to see how on your distribution, you're going to draw a line in the sand, and you're going to say, if my sample ends up on this side of the line, I'm going to decide that my treatment does nothing. If, on the other hand, it ends up on this side of the line, I'm going to conclude that my treatment is effective. So this is just a required boundary that we use in statistics where we say, all right, this is my line in the sand. And if you cross it, I'm going to say that the treatment is effective. If you don't quite cross it, then I'm going to say that the treatment is ineffective. And we'll see how we choose that cutoff score as we continue in this hypothesis testing procedure. But just so you know, we have to have this line in the sand, because otherwise we introduce human bias. How much of a difference is enough? So if we have that clear line that says, hey, you cross this line, and I'm going to say that treatment is effective, that is what's going to help us make those decisions. All right, so that's step 3. Step 4, we determine our sample score on the comparison distribution, and this is where those z-scores are going to come back. So we are going to compare our samples mean onto our comparison distribution from step 2. And spoiler alert, that comparison distribution is going to be a normal curve, which means we're going to go to appendix number 1, which means that we're going to have to deal with a series of z-scores. So we're going to have to take our samples mean and change it into a z-score. And then finally, when we determine our sample score on the comparison distribution, we then compare that to that line in the sand that we drew in step 3, and then we make our final decision on whether or not we're going to accept or reject the null hypothesis. So we compare our sample z-score that we calculated in step 4, and we compare it to the cutoff z-score that we figured out in step 3. And then the decision works this way. If the sample z-score is beyond the cutoff z-score, so your sample z-score crossed that line, then you say that we're going to accept the research hypothesis. We're going to conclude that our treatment does do something. Our treatment did make a difference, and we reject the null hypothesis. We reject the idea that our treatment does nothing. And you'll notice that every conclusion is accepting one hypothesis and rejecting the other, because they're complete opposites. If you accept the research hypothesis, you have to reject the null hypothesis. So if that sample z-score crosses that line, right, that sample z-score walks across that line and ends up here on your comparison distribution, you're going to say, I accept the research hypothesis. My treatment is effective. And I reject the null hypothesis. I reject the idea that my treatment does nothing. On the other hand, if your sample z-score kind of walks up to the line but then stops, doesn't cross over, it kind of stays here on this side, in that case, we're going to accept the null hypothesis. We're going to say, well, looks like my treatment does nothing, and we're going to reject the research hypothesis, reject the idea that our treatment does something. So, those are the 5 steps for the hypothesis testing process. That was kind of the general view or the general overview of that procedure. So now what we're going to do is we're going to take a look at how we would apply that to the situation we introduced earlier. So once again, you've been called in to help an elementary school the administrators of that school are worried about their students and their self-esteem levels. And when you come there, you notice that they have a very traditional physical education program, and your treatment is to implement a games program that you have designed to increase the self-esteem of these children. And what we want to know is that after playing that games program, is the population of children that played a games program, is it higher in self-esteem than the normal population of children? Or does your sample results indicate that the population of children who played that game are no different than the population of children that have a typical physical education program? Those are the questions we're asking. We want to know whether or not your treatment of this games program would be effective if you applied it to the population of students. All right, so let's get going here. So let's first set it up. This is kind of a typical description of an experiment. So I'll just read it out for you. It says, a researcher is evaluating the effectiveness of a new physical education program called the GAMES program for elementary school children. The program is designed to reduce competition and increase individual self-esteem. A sample of 16 children is selected and children are placed in the new program. After 3 months, each child is given a standardized self-esteem test. For the general population of elementary school children, the scores on the self-esteem test form a normal distribution with a mean of 40 and a standard deviation of 8. So first off, notice that we know what the general population of students who are not in the games program, who have not been treated, who are typical elementary school students, we know their mean and their standard deviation. The second thing to notice is that this sample of 16 children, we did not measure them before we applied the program. We measured them 3 months after we applied the program. That is typically not done. And just so you know, that's just to introduce the idea of hypothesis testing, just to make it a little bit simpler. Don't let it bother you. Don't think that this is a poorly designed study. This is for kind of introductory purposes only. So we have these 16 children. We give them the games program. After 3 months, we test their self-esteem. And we know that on this self-esteem test, the normal population, the typical population, has a mean of 40 and a standard deviation of 8. So we find that our sample mean is 43.5. Is this enough to demonstrate a significant effect? What a significant effect means is that is our difference true of the population? Does the difference in the sample generalize to the population? So that's the important question, because we can very easily just take a look at these numbers here and say the mean of my sample, their self-esteem is 43.5. The mean of the population is 40, right? This is grade 2 math right here. 43.5 is larger than 40. So it's easy to say that our sample has a higher self-esteem than the average student. However, what we want to know is that, is this a significant effect? That is what's true of our sample true of a population? Meaning, if we treated the entire population, would we get that same result? And that's what we're going to be doing in this hypothesis test. So the last thing we're going to do is we're going to assume a two-tailed test with an alpha of 0.05. A two-tailed test simply means that we're looking for a difference in either direction. So maybe it'll go up, maybe self-esteem will go down. We don't know. We're just going to do it in either direction. And again, that's something we'll get more into as we introduce hypothesis testing. But for now, let's stick to the basics. Is there a difference? Did our treatment do anything? Is it significant effect? That is, if we applied this treatment to the population of children, would that population change? All right, so we start off with the 5 steps. We're going to be doing this for every hypothesis test. So first step, restate the question as a research hypothesis and a null hypothesis about the population. So we want to know, is there a difference between the game program students, the population of game program students, and the general student or untreated population? Is there a difference between a population of children that have been playing the games program in terms of self-esteem versus a population of children that have not been treated with this program? That's what we want to know as psychologists. In order to apply physics to this, we need to change it into a research hypothesis. And the research hypothesis is that your treatment does something. It has an effect. So here's our research hypothesis. The treatment has an effect. And we write this by saying that the mean self-esteem for the students in the population that plays the game, so remember, this is always population. So the mean self-esteem for the games students is not equal to the mean self-esteem of the general students. So their mean self-esteem is not the same. Their average self-esteem is not the same, which means that there is some difference. Your treatment has made an effect, right? Your treatment has changed these normal students into these game students, and those game students are really different. Their population mean is different. The null hypothesis is the complete opposite. So the research hypothesis is that the treatment does have an effect. Null hypothesis is that the treatment has no effect. So we write this out by saying that the mean self-esteem for the games students is equal to the mean self-esteem for the general students. So the population of students that have been playing games would have the same self-esteem as the population of students under the general education program, physical education program. So the treatment really does nothing for self-esteem. So those are the two hypotheses. Now we're ready to go on to step 2. So step 2, determine the characteristics of the comparison distribution. The most important thing to remember right now is that if you are dealing with a sample size of 1, your distribution of sample means is the same as your population distribution. That's why the textbook starts you off with a sample size of 1. We're going to jump right into dealing with samples, dealing with a more realistic situation. So we're dealing with a distribution of sample means that is different from the population distribution, and we see that because it changes as your size of your sample changes. So we need to determine the characteristics of the comparison distribution. We're going to put a pin in this. We're going to see how to do this next chapter. For right now, I will be providing you with this information, but just be aware, kind of drive it into your head, make it a part of your go-to knowledge that the comparison distribution is different from the population distribution as soon as you have a sample. And you can see this in the fact that the population distribution had a mean of 40 and a standard deviation of 8, and our comparison distribution, while it still has the same mean, has a different standard deviation. So we'll see how to calculate this when we get to chapter 6. For right now, step 2 is done. I'll give you that information. All right, step 3, set a cutoff sample score or a critical value. This again is your line in the sand that you're going to compare your sample mean to. So if it crosses the line, you reject the null hypothesis. If it doesn't cross the line, you accept the null hypothesis. And we're going to see how to do this very soon. But for right now, I'll give you that information just so you can see how it works. And our cutoff score, because this is a two-tail test, is going to be positive and minus 1.96. And again, we'll see exactly how we get that information. But importantly, this is our cutoff scores. We got 2 lines. You go too far one way, we say that the treatment is effective. You go too far the other way, we also say that the treatment is effective. Those are our lines in the sand. And then, penultimately, step 4, we got to determine our sample score on the comparison distribution. And this is the first kind of mathematical calculation we need to do because we need to figure out our sample's z-score. So we have our sample's raw score. We measured their self-esteem. But if we want to be able to use that appendix number 1, which is in terms of z-scores, we have to change our sample score into a z-score. And we also have to do this because on step 3, our cutoff scores are in terms of z-scores. So step 4, we have to take our sample mean and we got to change it into a sample z-score. So this is stuff we've done before. All your practice on z-scores is finally paying off big time. So we have our sample mean, 43.5. This was the mean that we measured in the experiment. We gave 16 students this self-esteem test. We scored their test. We took their average. They had an average of 43.5. The comparison distribution has a mean of 40 and a standard deviation of 2. And it's important to remember that we need to find our sample's position on a distribution of sample means. So we have a sample mean, we got to compare it to sample means. That's why we're using the comparison distribution. But from here on out, we use our z-score formula. We plug in our values, 43.5 for the sample mean, 40 for the comparison distribution mean, 2 for the comparison distribution standard error, and we end up with a z-score of 1.75. So we have a z-score of 1.75. That's the position of our sample on that comparison distribution. So now what? Now we reach the final step. Step number 5. We decide whether to reject or accept the null hypothesis. And the rule here is, if the sample z-score is beyond the cutoff z-score. So what we mean by beyond is that if you start at a z-score of 0 and your sample z-score goes beyond, starting at 0, your sample z-score goes beyond your cutoff scores. It crosses that line. If that's what happens, you're going to accept the research hypothesis. You're going to say, yes, there's an effect. You're going to reject the null hypothesis. You're going to reject the idea that there's no effect. If, on the other hand, the sample z-score is within the cutoff z-score, so this is your line in the sand, and you start at 0, and you start moving towards it, and if your sample z-score stops you right there before you cross over, then that means that we accept the null hypothesis. We accept the idea that our treatment does nothing, and we reject the research hypothesis. So what do? Well, we take a look at our scores. So our sample score is 1.75. So our sample score is 1.75. Our cutoff score is 1.96, right? So starting at 0, if you start at 0, this is 1.96 and this is 0, you go to 0.5, you go to 1, you go to 1.5, you go to 1.75, you reach right there. So your sample score kind of walked all the way up, and it came close to the line. It's almost there, but it didn't cross the line. Your sample score did not cross your cutoff score. So what we do is we look at this and we say, if the sample score is within the cutoff score, your sample score didn't quite make it and cross that cutoff score, what do? We accept the null hypothesis. We reject the research hypothesis. So that's what happened here. We accept the null hypothesis, and we conclude that the games program does not change self-esteem of students compared to the general education program. So this is an example of hypothesis testing from start to finish, going through all 5 steps, and the final conclusion here is that even though the self-esteem of our 16 students is higher than the self-esteem of the general population, right? 43.5 is higher than 40. We cannot generalize that that's going to happen to the entire population. We can't generalize from our sample to the entire population because the difference was just not big enough. And this is, again, the testing procedure that we do. We know our population is higher than 40, we know our sample is higher than the population mean, but when we try to generalize that, this hypothesis testing procedure is saying, no, that is just true of your sample, right? That's just a fluke sample that you ended up with. It's not going to be true of the entire population. So that's the conclusion that we would have from this particular hypothesis test. So this is a bit of a downer. It's always a downer when you don't get to reject the null hypothesis because that means that your treatment is ineffective. But that's part of the reason that we have this hypothesis testing procedure. But wait, let's throw in one little wrinkle into this just to illustrate the flip side of the hypothesis testing procedure. Let's say that we just finished analyzing our data. And once we discovered, oh no, we're going to accept the null hypothesis. Oh, our treatment doesn't do anything. I spent years working on this games program, and the first time we go out into the field, the research suggests that it does nothing. My treatment is ineffective. Oh my goodness, this is horrible. Back to the drawing board. What are we going to do? Let's say that at that point you hear a knock on the door and one of your grad students bursts in and says, oh my gosh, I ran all the way from home. I am so sorry, but when I was scoring the tests, when I was scoring the self-esteem tests for the sample of 16 children, I don't know what happened, but I forgot to add 1, right? Oh man, I'm so sorry. But their mean of 43.5, that's the wrong mean, right? I'm really sorry. Their mean is actually 44.5. So let's say that occurs. The mean is actually 44.5. So now we have the exact same procedure, the exact same test, but we're dealing with the correct mean now of 44.5. Let's see what that does to our hypothesis testing procedure. All right, step number 1. So it's still the 5 steps. We still go through the 5 steps, and get used to these 5 steps. You're going to be seeing them over and over and over again. So very nicely, we don't have to redo everything, because you take a look at step 1. We are still interested in the same question. We still want to know, is there a difference between the game program student population and their self-esteem versus the general untreated population and their self-esteem? That's still what we're looking for. Does our treatment change the population's self-esteem? So therefore, the research hypothesis and the null hypothesis, they're not going to change. Research hypothesis is still that the games do have an effect. Your treatment does something, and that's still going to be that the mean self-esteem for the games population does not equal the mean self-esteem of the general population. So your treatment does something. The null hypothesis is still going to be that your treatment has no effect, that the game students population is going to have the same self-esteem as the general student population as well. So step number 1 doesn't change at all. Step number 2, determining the characteristics of the comparison distribution. Still remember, one more time, we'll keep drilling this into our minds. Your population distribution is only the same as your distribution of sample means when your sample is the size of 1. As soon as you get into more than 1, like 16 subjects for our example here, your distribution of sample means what you compare your sample to, that changes. So make sure that you keep that in mind. It's going to become more and more important as we move on. So we're going to be determining the characteristics of our comparison distribution in step 2. We're going to learn how to do that next chapter. For now, I will be giving you that information. And lo and behold, it's still the same as we had it in the first go through. So it's still got a mean of 40 and a standard deviation of 2. That's our comparison distribution. Step number 3, we set a cutoff sample score or critical value, a line in the sand that we're going to compare our sample mean to. And thankfully, this has not changed. So we'll see how to do this very soon. But these lines in the sand have stayed the same. So far, nothing much has changed for this new analysis based on our corrected sample mean. So what is going to change? Well, step 4 is going to change, because we have to find where our sample is on that comparison distribution. We have to find if our sample has walked up to the line or has our sample crossed over the line that we determined in step 3. So we determine our sample score on the comparison distribution. We got to find out that z-score. So now we use the corrected data. Our mean is 44.5, not 43. Remember that, grad student, it's 44.5. Our samples, our comparison distribution has a mean of 40 and a standard deviation of 2. That's what we got from step 3. So now putting that all together into our z-score formula, we substitute in sample mean, comparison mean, and comparison distribution, standard deviation, do our crunch our numbers, and we get a z-score of 2.25. So this is a different z-score than the first time through, again, because our sample mean has changed, so its position on the distribution has changed. Now it has a z-score of 2.25. So then finally, we have to make our decision. We go to step 5, and now we go, if the sample z-score is beyond the cutoff z-score, we're going to accept the research hypothesis, and we're going to reject the null hypothesis. So if this is your cutoff, and our z-score for our sample has walked past that cutoff score, we're going to say, haha, you've crossed that line, you've gone beyond the cutoff score, we're going to accept the research hypothesis, we're going to reject the null hypothesis. If, on the other hand, the sample z-score is within the cutoff score, if it kind of walks up to that cutoff score and then stops, doesn't cross that line, we're going to accept the null hypothesis and we're going to reject the research hypothesis. We're going to accept the idea that our treatment again does nothing. Oh no, back to the drawing board. And we're going to reject the idea that our research did something. So which case is it this time around? Well, remember that our cutoff z-score was at 1.96 and our sample z-score is at 2.25. So starting at 0 here, we walk, we pass 0.5, we pass 1, we pass 1.5, and then importantly, we pass our cutoff score, right? This is 1.96, right here is 2, right here is 2.25. So in this case, our sample walked past that line. It has crossed that line. And if you take a look at the decision for step 5, you cross that line, we reject the null hypothesis, we accept the research hypothesis, and that's what we're doing in this situation here. So completely different conclusion. So previously we concluded that our games program does not work. It does not change the self-esteem. But now that we have the correct data, we come to the complete opposite conclusion, and we conclude that the games program does change the self-esteem of students compared to the general student. It does change the self-esteem of the population of students that play the games program versus the population of students that don't. And this is hypothesis testing in a nutshell. And this also illustrates why it's so necessary to have a system like this that allows us to make objective decisions. Because if I was to tell you beforehand that a 1 point difference would mean the difference between saying this is an effective program versus this program does nothing, that's hard to believe. But as you can see here, hypothesis testing, you draw that line in the sand, you find out where your mean is, and if your mean doesn't cross that line, you say that your treatment does nothing, you accept a null hypothesis. But if it does cross that line, you say that your treatment is effective and you reject that null hypothesis. All right, so that was it for today for this special online class, the Introduction to Hypothesis Testing. Thanks for joining me, and let this hypothesis testing idea kind of become familiar to you. Just kind of let it, do its work on your mind, because this 5-step procedure is what we're going to be doing over and over and over again. We're going to get more into why those steps exist. We're going to get more into some of the variations on some of the steps, but it's going to be these 5 steps over and over and over again. And one of the nice things about hypothesis testing, especially in the beginning when you're learning statistics, is that you might not understand everything about why we do the 5 steps. You might not understand why the comparison distribution is the way that it is, or why if you cross the line you accept you reject a null hypothesis. If you don't cross the line, you accept a null hypothesis. That'll make sense later on. But it's very nice to know that we have this 5-step procedure where as soon as you learn that 5-step procedure, even if you don't understand the mechanics of it, you can still do hypothesis testing. So that's what I want you to kind of concentrate on right now. We'll get into more of the explanation of why everything is working. But for right now, just kind of get used to that idea of we're going to do these 5 steps. We're going to find out where our cutoff score is. And we're going to find out where our sample is. And if our sample does not cross the cutoff score, we're going to accept a null hypothesis, say that our treatment does nothing. But if that sample crosses that line, we're going to say, oh, you crossed the line, treatment does something. And that's the essence of hypothesis testing. So that's going to be it for today. Thanks for joining me. And again, make sure that you kind of let this become a part of your mind, kind of, grab hold on tight on it. If you got to watch this video more than once, please do so, because this is going to be it for the rest of the semester. So welcome to the ninja part of statistics, and I will see you in class next time.